Hello, and welcome to lesson 9.3. All right, buckle up, because we've got some stuff to talk about. Okay, so in lesson 9.3, we're going to be looking at solving rational equations, and we're going to look at some what we call naked problems, which is just algebraic equations. You just solve them and then done. Okay, and then we'll be looking at some application problems of how to use these equations to solve real life problems. So first, before we get into real world problems, I just want to talk about the fundamental idea for solving rational equations. Okay, it's pretty simple. In order to solve a rational equation, just multiply by something so that all the denominators go away, so that they're canceled. All right. Now, the most effective way to do this is to identify the least common denominator and then multiply everything by that LCD. You could find a common denominator, but you're probably going to make it more complicated than it needs to be. So just stick with identifying your LCD, multiply by that, and then you'll have an equation that you're pretty familiar with on how to solve. And most of these equations, you will be able to factor and find the roots, okay, using some factoring techniques you've done before. This is a reminder here to not forget to check for extraneous solutions, okay? Because we're dealing with rational functions, right, like 1 over x plus 5, if I got x equals negative 5 as part of my solution set, well, negative 5, if you put it back into the original, that's negative 5 plus 5, that's division by 0, which is undefined, right? And so if I get an undefined value like that, well, that's not part of a solution set, right? That's wrong. It doesn't solve the equation. It's not true. So be careful. We check for extraneous solutions the same way we always have, just plug it back in. But really, all you really need to do is see if it makes the denominator 0. Okay, you don't actually have to carry out the entire calculation usually. If you just see if the denominator is 0, that's pretty good for rationals, okay? And lastly, I would like to introduce a new notation for you that you may have not seen before. Now, in the past, a lot of times we've written just no solutions, or sometimes D and E, meaning does not exist. First, when we have no solutions that satisfy an equation, I'm going to introduce a new symbol for you to use if you would like, and maybe to try and recognize these as answer choices, either on your homeworks or quizzes or tests, because I just want you to see some of the formal mathematical language. So instead of writing no solutions, often we will write the solution set as this symbol right here that I've circled, kind of denoted like this. This symbol is called phi. You see, it says this symbol is read as phi, pronounced phi. I think sometimes people call it phi. I think it's supposed to be phi. I think that's the official whatever. But, I mean, whatever. Okay, who cares? It's not a big deal. Yeah. Well, it'd be kind of funny if you called pi, instead of calling pi, you called it p. Right, I don't know. Anyway, so this symbol, phi, means the empty set. And the empty set is essentially a set with nothing in it. So when you write something like x equals phi, or x equals the empty set, this is like saying that the solution set for x is the empty set, or in other words, there's nothing in the solution set. Phi, this thing, is defined to be the empty set. And I'm not missing anything. There's nothing written here. That is quite literally empty. There's nothing in that set, okay? So it's just a fancy way of saying no solutions. Okay, now that we've got that, let's work a couple examples and just work them out, yeah? So I mentioned earlier that you want to clear all of your denominators. So let's looking at example 1. I notice I got a denominator of x minus 3, and that looks like that's the only denominator here. I suppose you could say that this 1 over 1, but, well, who really cares about that, right? So I'll say that my least common denominator is going to be x minus 3. So what you're going to want to do is multiply everything by x minus 3. Multiply both sides by x minus 3. And so this is like saying I'm going to take x plus 4 over x minus 3 plus 1. And I multiply that by x minus 3. This equals 7 over x minus 3 times x minus 3. I'm just multiplying by the LCD on both sides. Now, look, if you distribute this here and to the 1, well, when you distribute it to x plus 4 over x minus 3, the x minus 3's cancel, and I'm just left with x plus 4. And then if you distribute it to the 1, well, that's just plus 1 times x minus 3, right? And you don't really have to write the 1 there, of course. And then the same idea here, these x minus 3's cancel, and I'm just left with 7. So you've cleared all denominators, yeah? So I'll go ahead and distribute this 1. That just says x plus 4 plus x minus 3 equals 7. Did I do that right? I think so. Okay, so yeah, 4 minus 3, I'm sorry, I don't know why I'm going slow on this. X plus x is 2x, and 4 minus 3 is positive 1 equals 7. Solving for x, you get 2x equals 6, which tells me if I divide both sides by 2 that x equals 3. Okay, and that would be my solution. Except you got to check for extraneous solutions. So take this and say, uh-oh, if I have x plus 4 over x minus 3 plus 1 equals 7 over x minus 3, if I plug in 3, I get 3 plus 4 over 3 minus 3. Oops. Hello, that's 7 over 0, which is undefined. So actually, by checking for extraneous, I say, uh-oh, no. I say 3 is extraneous because it causes division by 0. So therefore, I know I'm writing it up here, I say x is the empty set. This, again, this is a way to write no solutions, okay? Alternatively, you could write x equals that. Quite literally, that would be true, okay? That would be true. X equals nothing. X, that's what that says. X is nothing. There's no solution that makes this work. Okay, let's take a look at example 2. And this one's a tad more complicated. Now, remember, I said it's most effective to identify your least common denominator first and then multiply by that, right? So let's actually factor all denominators. Make sure they're factored. I'll say that this is 5 over, I can factor out a GCF of x squared and get x plus 5. This equals 4 over x plus 5 plus 1 over x squared. So therefore, my LCD, least common denominator, well, if I look at this first denominator, I know I need an x squared. And then I know I need an x plus 5. And then when I go to x plus 5, well, I already have that in my LCD. When I go to x squared, I already have that in my LCD. So I'm good. So that is the LCD. So let's multiply this entire thing by x squared times x plus 5. So maybe I'll use this in blue. I say multiply by LCD, because I don't want to write all that again. So I'm just going to put a big old parentheses like this and say times x squared times x plus 5. And keep in mind, I'm distributing this to everything. So you're distributing this here, you're distributing this here, you're distributing it here. Now what I want you to notice is, I'll get my laser pointer, this guy, if I put that here, then I have 5x squared x plus 5 over x squared times x plus 5. So those just cancel, which means I really just have 5 here. So I'm just going to do that. Say just 5. Don't bother writing all that out. You can do that in your head, right? That stuff just cancels out. And then the same thing idea here, if I distribute x squared times x plus 5, if I put that here, well, then that's 4 times x squared times x plus 5 over x plus 5. But those cancel. So really all I need to write is 4x squared. So, boom. And then plus, and then last, and I'm going to do it again, I know. You probably caught on, but I'm distributing this here. So that's 1 times x squared times x plus 5 over x squared. The x squareds cancel, so it's just x plus 5. So say plus x plus 5. You don't have to put parentheses around it like that, but I did, just for the sake of it. And so now this is a quadratic that I can solve for. If I subtract 5 from both sides, I get 0 equals 4x squared plus x. You see, because I've subtracted 5 on both sides. You might say, oh my God, how do I factor this, Mr. Spake? This doesn't look familiar. Yes, it does. That's just GCF. X times 4x plus 1. That's fully factored form, which means you can identify the roots. Yeah? I'll say the zeros or solutions. See, I never know how to write zeros. Is it R-O-S, R-O-E-S? I actually think it's both, and I can never decide which one I like. Anyway, the zeros are x equals 0 and 4x plus 1 equals 0. But if you solve for x here, that's just x equals negative 1/4. And I'll let you I'll let you plug that, solve that if you don't see it. Anyway, those are my solutions. But remember to check for extraneous. So check for extraneous. Now, if I do this, you don't have to write this, guys. You can just plug in these numbers to the denominators to see if anything happens. Observe 1 over x squared. And I'll use yellow here. See this 1 over x squared? 1 over x squared. Well, that equals 1 over 0 if x equals 0. Right, it's 1 over 0 squared. And that's undefined. So, therefore, x equals 0 is extraneous. And then you can plug in your 1/4, your negative 1/4, and everything will be fine. Okay? Just trust me. Look, none of the denominators go to 0 if you plug in negative 1/4. And if you don't trust me, just use a calculator and do it. And keep in mind that you can use the store feature. Okay? You can store this value for x, type in this side of the equation, evaluate, then type in this side of the equation and evaluate, and make sure, verify that they do both work out. I'm not going to do that here because this video is not about checking extraneous. It's something we've done before, but if you need a reminder, just let me know in class, okay? We do end up finding, therefore, the solution set is x equals negative 1/4. Okay? All right. Okay, so that handles solving the quote-unquote naked problems, just being, the typical problems you're going to run into. So basic gist, identify LCD, multiply throughout the LCD, solve as normal, and then check for extraneous. Okay. Application problems. Now, this is where the real meat of the video is. We're going to dedicate a lot more class time to this, so this is really just a slight introduction to it. If you don't 100% grasp the idea of this after watching the video, that's okay, all right? That's okay. I honestly don't expect you to. If you do, that's fantastic. That's great. You're prepared for class. That's wonderful. But if you walk away from this saying, I need some more time with this, perfectly understandable. All right, this stuff is tricky. So, I'll say that perhaps the most difficult part of solving these real-world applications isn't actually the mathematical solving, it's the setting up of it. The setting up can be quite tricky. You want to give some careful thought about your variables and pay attention to what the question is asking. I'd say that it's a really good idea to write down what your variables are and try to establish some relationship between them so that you understand what's going on. Okay, so I'm going to look at example 1. There's kind of 2 main types of rational problems you're going to run into. I suppose there's more than just 2, but these are the 2 main ones you're going to see, okay? And the first is called a work rate problem. Now, a work rate problem is essentially just some task is getting performed in some amount of time, okay? So it's kind of like, I don't know, your work equals some task accomplished in some amount of time. All right, it's like how many things can you do in a certain amount of time? And I know that sounds kind of silly, just like, what do you mean by things? Well, let me show you. Okay, so Catherine can paint a house in 15 hours, and Dan can paint a house in 30 hours. So the question asks, how long will it take Catherine and Dan to paint the house if they work together? Yeah. So 2 things are happening here. We're kind of combining the rate of painting from Catherine with the rate of painting with Dan. Okay. So here's what I'll say. Catherine. Okay. What can Catherine do? She can paint one house, because it says a house. She can paint one house in 15 hours. And then Dan, well, he can paint one house in 30 hours. You see, the task is painting a house. And it's not painting multiple houses, it's painting one house. And you do need to pay very close attention to this, because notice that the question does ask, how long does it take for them to paint a house, the house, if they work together? You want to be very careful with that, because the question could ask, it could give you, hey, this is how long Catherine paints one house. This is how long Dan paints one house. How long will it take them to paint 5 houses together? Okay, so do pay attention to what task is being accomplished, okay? In this case, it's not a big deal, but I caution you to be very careful with that. Now, if I look at them together, right, Catherine and Dan, this is Catherine plus Dan, right? Because they're put together. Their rates are combined. They're put together, so we add their rates together. Well, they're going to paint one house. That's the task. And the question is, how many hours? So I don't know what you want to call this. I'm going to use the variable t for time. I'll say t hours. You could say h hours. It doesn't really matter. So yeah. So Catherine, together, they paint one house in t hours. So you see, one house in t hours equals a combined rate of Catherine painting it one house in 15 hours plus Dan painting it one house in 30 hours. That's your equation. Okay? That's it. And you see, that's actually a pretty simple rational equation, right? The math isn't quite crazy here. So let's combine these. 1/15 plus 1/3. Well, you can get this is pretty typical math here. That's like 3/30ths. Is that right? Because if I double this, right, that's 2/30ths plus 1/30th equals 3/30ths, which if you divide, 3 over 30, that's 1 over 10. And then that equals 1 over t. Oh my God, why did I write t again? Stop that, Mr. Spake. 1 over t. And now that you're here, you could just do cross multiplication. 10 times 1 equals 1 times t. Therefore, t equals 10 hours. Okay. I could paint it in 10 hours. Yeah. I think that's right. I don't think I made any mistakes. I'll double check after the video. But yeah, it's really not that bad. But you do want to make sure you label all these pieces of information. It'll vastly help you set up the problem, because if you just try to jump to this step, that can be difficult. That can be tough. Okay, example 2, uniform motion. So uniform motion is, well, it's just the idea that an object's traveling on a linear path. It's traveling in a straight line somewhere, ideally at a constant velocity or speed. Now, it's not super necessary for it to be like totally constant, because that's not realistic, right? If you're driving a car for 80 miles an hour for 3 hours, maybe you average 80 miles an hour, but you're not actually driving that the whole time. So often these problems will give you their average speed over some interval. Okay, whether that interval is time or distance, they'll give you their speed like that. Now, it's really important with these problems to understand this equation. Speed equals distance over time. Okay? And you're going to use that. You know that equation because that's what speed is. Duh. But you sometimes have to manipulate that equation to figure things out. You see, so if I say that speed, I'll say that's v, that's d and t. I'm going to use v for velocity, okay? Velocity is distance over time. Well, then if you wanted to figure out time, then time is distance divided by velocity. And if you wanted to find distance, distance is velocity times time. And so you can use these three equations to set up these problems depending on the information you're given. Okay, so let's look at what we're given here. Tim paddled his kayak 20 kilometers upstream against a 3 kilometer per hour current and then back again in 5 hours and 20 minutes. Now we ask, how fast is Tim's speed in still water? Okay, there's a lot of pieces here. So first of all, let's address what they're asking us. How fast is Tim's speed in still water? That's what we're solving for. So let's call x Tim's speed in still water. And if you're not sure what that means, here's what's happening. Tim's in a river, right? Here's Tim. He says, hi, right? And he's paddling along this river. Now, look, he's paddling upstream, so the current is pushing against him as he goes upstream. So if he's going upstream, there we go. But then he's going to paddle downstream. So what's happening here is the current is going to push against him, but it's also going to push with him. Against on one journey, with on the other. And that's important. And what we're asked to find is Tim's speed in still water, meaning if the current didn't exist, if there was no push or flow from the current, either pushing against or with him, how fast would he be paddling? Okay. So that's what we're looking for. Now, what other information I have? I have total time, right? It says that total time is 5 hours and 20 minutes. Now, you're probably not going to use those units of measurement. So you either want to use a decimal or a fraction. Okay, now, Mr. Spake likes fractions. So if you want decimal form, well, 20 over 60, isn't that 1/3? So, yeah, I don't know if you want to use decimals here. That's like 5 hours, 0.3 repeating. I would probably do this. You could say it's 5 1/3, but Mr. Spake, he's going to say 16/3 because that's honestly easier to manipulate when doing the algebra. Okay, so it's 16/3 hours if you're expressing it, because you gotta choose a measurement of time. Yeah, either convert everything to hours or convert everything to minutes, and it's probably easier to just deal with hours since our speed is in kilometers per hour. Okay, now we do see that the speed of the current that's 3 kilometers an hour. Yeah. You see how I'm writing down every piece of information before doing anything? This is a really important process that will help you a lot. Trust me. Okay. What else do we know? Well, we know his distance upstream is actually the same as his distance downstream, right? His distance upstream is 12 kilometers. So I say that's 12 kilometers. And the same thing for going downstream, actually. Downstream. That is also 12 kilometers. Okay. Now ask ourselves, how fast is he paddling upstream, right? What is Tim's speed upstream? Well, we don't really know that, but here's what we do know. We know that it's how fast he's paddling in still water, being pushed with or against the current. So Tim's speed upstream, the current is pushing against his speed. So it would be Tim's speed in still water, but 3 kilometers an hour of current is going to push against that, which means it's going to subtract from the speed he would be doing if he were in still water. Then we look at his speed downstream, and I'm sure you can set that up. That's going to be x plus 3, because that 3 kilometers an hour is going to add to his speed. It's going to push him along with the stream. Okay, so you've got all this wonderful information about all this business. Okay, and you know what? I'm gonna erase this, and I'm gonna take the lasso tool here, put that here. Okay, all right. You know what? I'm gonna switch to blue so it's not overloaded with red. Now, we know total time, so if you can add the time spent rowing upstream, and you can add that with the time spent rowing downstream, then that's going to equal his total time. Yeah? And if you look at the equations we wrote over here, time can be expressed as distance over velocity. You see, time equals distance over speed. And maybe, I'll just write that as time. So his time upstream is going to be his distance upstream divided by his speed upstream, right? So really, if you want to rewrite all of this, you don't have to do this, but I just want to lay this out for you. His distance, I don't need to write, his distance up divided by his speed up plus his distance downstream divided by his speed downstream equals the total time spent, which would be total distance over what? What would that be, right? I don't know. What do you tell me? Think about that. Yeah? Okay, so I'm going to check my key real quick because I don't want to set this up wrong for you guys, okay? I know you're saying, Mr. Spake, you're cheating. And I say, yeah, but I don't want to give you the wrong thing. That's all. And it seems that I lost my key. Is that so? Did I really lose it? Oh no, I'm wasting precious time. Yeah, total distance over his speed. Well, oh, I'm sorry. You see, I was having a brain fart. Okay, look, I don't need my stupid key. What am I doing? Mr. Spake, what are you doing? I'm sorry. I was getting confused with myself because it's like, well, we don't have his total speed. We don't have his average speed for the whole trip or whatever, right? We don't actually need that because we found total time. Dummy, it was 16 thirds. So that's still total time. See? Even just goes to show you, even Mr. Spake needs a second to think about these sometimes. Okay, you got to be really careful. We know the total time because it was given to us. So we don't have to worry about converting that time to distance over speed. Okay, so anyway, his distance upstream, that was 12 kilometers over his speed upstream. That was x minus 3. Plus his distance downstream was 12 kilometers over his speed downstream. That was x plus 3. Equals the total time he spent was 16 thirds. And now, this is an equation I could solve. So do you see how the brunt of all of this was just setting it up? It wasn't even doing the solving piece, right? Yuck. Okay, so let's identify the LCD. I'll switch to yellow here. Let's just solve the rest in yellow. Your LCD is going to be x minus 3 times x plus 3, and you need a 3, okay? So you're going to multiply this whole thing times 3 times x minus 3 and x plus 3. I'll let you go ahead and do that. If you want to pause the video, figure out what that is. But that's going to end up being 12 times 3 times x plus 3 plus 12 times 3 times x minus 3 equals 16 times x minus 3x plus 3. Okay. Now, I'm going to do some fun algebra here. I'm actually going to think creatively here. 12 times 3 is a common factor. That's 36. I'm going to factor 36 out, and then what's left inside is x plus 3 plus x minus 3. And those 3's cancel. So it's really 36 times 2x, which is 72x. Okay? Equals, and then if you expand that, that's a difference of squares. That's x squared minus 9. Okay? So then I'll divide both sides by 72. Oof. Wait, do I want to do that? Think about that, Mr. Spake. I don't know. Does 16 go into 32? Where's my... Okay, let me... Where's my calculator? Ugh, this is the worst video ever. I'm so sorry. I was totally just... This is not time efficient. 4.5. Yuck. How about 8? Okay, I like that. Okay. I'll just divide both sides by 8. Make it a little bit prettier. Divide by 8. Divide by 8. Okay? Therefore, I get 9x equals 2x squared minus... It says it's 2 minus 18. Okay. All right. I hope you're following along with what I'm doing here. I have no space. I hate this. No space. Lasso. Say, Mr. Spake, you're a crybaby. Just solve the problem. And shush already. I say, I'm tired, okay? I'm tired. Minus 9x minus 18 equals 0. Oh, I don't want to do factor by grouping. What is that? 2x and I'm going to guess 6 and 3. Is that going to work? How about 9 and 2? 18. That is factorable, right? 2 times 6 is 12. This is 3, so that's negative. Boom. Booyah. Got it. Got him. All right. So then you set this equal to 0. You set this equal to 0. And x equals, negative 3 halves. And x equals 6. Now, put this back in context. You found your answers, right? Thing is, x is Tim's speed in Stillwater, and speed is not negative. So that doesn't make sense because speed is not negative. Oh my God. Would you write good? Negative. Therefore, x is 6. Okay? Therefore, x equals 6, and it should be kilometers an hour. That's the speed in still water. Done. Oh my God. I just want the 3 dots to be nicely aligned. Okay, sorry I sound so done with this problem. It's just, I just hate that this took so much time. I'm sorry I made the video long. I told you I'd stop doing that, and I feel bad. So, sorry, but also this stuff is hard, and you need to see it. So there you go. That's the problem worked out. Okay. You have one of those on your homework, I think. And we have a ton of these on our homework coming up. Like a ton. Like so many. Like literally so many. Okay. So anyway, enjoy the rest of your night. I hope you enjoyed the video. I'm sorry for taking so long and just being all over the place. Maybe I'll be better in the future. Okay. See y'all in class.